Welcome to today's session. Fast forward your product launch using ESL methodologies. Let's first talk about what are ESL methodologies. ESL is a term which has been used in the industry since long time in various different contexts. It can be defined as a combination of two broad phenomena. One is designing of the complete system including hardware and software instead of just focusing on the hardware design. Second is raising the abstraction of chip design above RTL. These are enabled using the high-level language like C, C++, Python, or the standards like System C, UPF 3.0, IP-Exact, and Portable Stimulus. ESL methodologies are not supposed to replace the traditional RTL to GDS flow. These has to rather coexist and augment it further. These enables us to perform various operations which are not typically feasible using the traditional methodologies like pre-silicon firmware development, architecture analysis and optimization quite early in the cycle, high-level synthesis, SoC and system level simulations. One of the most widely used applications of the ESL is the virtual prototyping. Virtual prototypes are the fast simulation models of the SoC or the complete system, and on top of these models we can run exactly the same software which we are supposed to run on the real hardware. These are the register accurate functional representation of the hardware developed using System C and TLM 2.0 and advanced modeling concepts like loosely timed temporal decoupling, etc. Virtual prototypes are used for software development and testing, hardware software integration and system validation, automating the regression for the firmware, or architecture design and exploration, etc. One of the primary benefits of virtual prototypes is that it allows us to start the software development quite early in the cycle, even before the RTL is available. Hence, it shortens the overall schedule of the project. It enables early feedback between the hardware and software teams, thus eliminating any ambiguity in the understanding or the specs quite early in the cycle. Compared to the hardware, these simulation models provide improved control and debug visibility. We can inject the fault through the software or in the model to test how the system is going to react in the corner case scenarios. These models are quite adaptive to the frequent changes. So if we have a change in the specs at a later stage, these can be very quickly incorporated into the models without requiring too much of rework or too much of cost. These scales more easily for the massively parallel testing. So we can run thousands of nightly regressions in parallel, or hundreds of embedded software engineers can work in parallel using these simulation models. These virtual prototypes are quite widely used already in some domains like automotive, storage, mobile, networking, etc. And will also be quite useful for emerging domains like IoT, artificial intelligence, deep learning. Another important use case is architecture exploration. For this, we have to develop the architecture models. The minimum that we require are the performance models and the power models. Performance models are mainly cycle approximate or cycle accurate transaction level models of the CPU, memory subsystem, interconnects, etc. For developing these models, we have to extend TLM 2.0 for specific bus architectures, and these models can be used to analyze and optimize the architecture for latency and throughput. Power models. So there are different techniques prevalent in the industry for developing the power models. One of the standard ways to use System C TLM models along with the UPF 3.0 overlay. So we can take the power consumption data from the IP datasheet or measurements from the past projects and overlay it on top of System C models using the UPF 3.0 format. These models can be used to analyze and optimize the architecture for the power consumption. Once we have the architecture models for our SoC or the system, then on top of it we can run the application workloads which are the model of the target software. So we can try to fine tune or optimize the architecture for specific target applications. There is also an open source framework Gem5 which is used for the architecture exploration and architecture modeling. It already have library of various CPU models supporting multiple ISAs like ARM, RISC-V, MIPS, x86, etc. And further, we can develop the model of our own CPU or the custom processors. It also have the reference models of the memory subsystems, which we can use as the reference and develop the model of our own memory subsystem. Gem 5 can also co-simulate with System C. So we can use both of them in the flow and try to use best of the both worlds. One of the emerging use case of ESL is high-level synthesis. It enables us to design the chips using the high-level language like C, C++, System C, and the RTL can be automatically generated using the HLS tool. These designs in the high-level language have 5 to 10 times lesser code and simulate 10 to 1000 times faster than the corresponding RTL, thus providing a significant boost in the productivity and significant reduction in the design efforts and further significantly reducing the possibility of introducing bugs in the design. With the same input design, we can generate the multiple variants of the RTL targeted towards different technology library or different application areas. HLS also bridges the hardware and software world, so it makes the vast pool of free C and C++ tools available to the chip designers. And moreover, we can use the existing C and C++ implementation as the starting point for the chip design. If we see today, most of the new SoC designs are happening in these emerging areas like computer vision, audio processing, 5G, artificial intelligence, deep learning. And in these domains, there is already lots of software implementations available either in the open source world or in-house inside the companies. So if we can define a methodology to seamlessly migrate these software implementation to the semiconductor chips, it can be a big game changer for the industry. At Circuit Sutra, we executed a pilot project using Mentor Catapult high-level synthesis tool. And in this project, we were able to migrate the existing open source software implementation to the semiconductor chips. We are further working on refining this flow and making it more mature. We talked about different use cases of ESL, virtual prototype, architecture models, high-level synthesis. All these use cases requires different kind of models developed at different abstraction levels with different accuracy of timings and the functionality. With the right set of adapters and transactors, we can combine different kind of models to create advanced ESL flows, thus enabling the powerful shift-left mechanism throughout the entire design and verification cycle of a SoC. There have been talk in the industry that why can't we have the same model for the HLS and the virtual platform. Now technically it's not possible to have the same model because for HLS we require a model which is synthesizable, and for virtual prototype we require a model which is as fast as possible. But if we start with the existing software implementation, then we can at least have the same starting point, and with the same existing implementation we can refine it to make it synthesizable for HLS, or we can wrap it in the TLM and system C and further use the modeling techniques like temporal decoupling and loosely timed to create the models for virtual prototyping. And further we can try to reuse the test bench and the test cases across these two different kind of models. We can further combine these with the RTL simulation, FPGAs, emulations to create a truly hybrid environment. And further we can create a verification setup which can actually flow from IP level to SoC level to system level. With these kind of setups, we get a complete flexibility that throughout the life cycle of the project, different teams can choose. I mean, depending on what portion of design is already available in RTL, what portions we have the system C models. So different team can actually choose different kind of technologies to enable a true verification continuum from IP level to SoC level, right from the beginning until the end throughout the design and verification flows. Further, with these kind of setups, we can do different kind of design space explorations. We can do hardware and software partitioning and the combination of like FPGAs, eFPGAs, HLS and virtual platforms. There are two very interesting phenomena happening in the semiconductor industry today. One is that new and innovative kind of SoC architectures are being designed for artificial intelligence and deep learning kind of applications. And second is the open source hardware movement. ESL methodologies are all set to play a very important role in the success of both these phenomena. These are essential to get the most optimum architecture at the minimum cost and achieve the fastest time to market goals. Let's talk about SoC for artificial intelligence and deep learning. These kind of SoCs have very specialized processing requirement. Instead of using the generic CPU cores, we need to have the purpose-built compute engines, which may consist of hundreds or thousands of CPU cores, each of them supporting a small number of instructions. It enables compute for data in motion through the data level and instruction level parallelism. A requirement is to support massively parallel and heterogeneous matrix multiplication. And further, we may accelerate the neural network algorithms as well. Another important aspect is to design very innovative memory architectures. Memory has to be tightly coupled with hundreds or thousands of CPU cores. Training the neural networks requires multiple GB of memories. Further, there is requirement for real-time data connectivity to get the data from the sensors and other sources. Hence, there is a requirement for huge on-chip and off-chip bandwidth. Further, while designing such SoCs, one of the requirement is that it should work on all frameworks without the software modifications like TensorFlow, PyTorch, ONNX, etc. So usage of virtual platforms become very important. Optimizing the performance is very important for the real-time edge applications. Power optimization is anyway very critical for battery-powered edge devices as well as the AI chip for the server, where the power consumption is a major portion of the cost. A high-level synthesis can be effectively used for accelerating the neural network algorithms. So we can see that all the use cases and all the aspects of ESL are very important for designing these kind of SoCs. At Circuit Sutra, we are conceptualizing the reusable modeling infrastructure and methodology, which can be used to very quickly develop the models for such SoCs. Open source hardware movement is mainly fueled by the RISC-V, which is a open source instruction set architecture. So RISC-V being a new ISA, anyone who is using RISC-V must be designing a new SoC. One of the important feature of RISC-V is that it allows you to add custom instructions. So people are using it to design their own custom processors which are fine-tuned for specific applications. And such custom processors are at the heart of the specialized SoC architecture. So deploying the ESL methodologies right from the beginning in such a project is very important. Our RISC-V ecosystem is still evolving. For the effective deployment of ESL flows, there is a need to have a very robust, reusable system C modeling infrastructure. One of the important components for the ESL flows are the CPU models. For the virtual prototyping use case, we primarily need fast instruction set simulators. So in the RISC-V ecosystem, there are several open source ISS available, like we have a Spike simulator, or Whisper ISS from Western Digital, or we have KEMU. So at Circuit Sutra, we developed the System C wrapper around these open source ISS. So these can be effectively used along with the System C models. Apart from that, there is also a commercial CPU model, OVP from Imperas, that can also be used along with System C. Gem 5 have a very basic RISC-V CPU model for architecture exploration and it can be enhanced further. We also need to have a well-defined process and documentation about how to add the custom instructions to these CPU models. So the CPU model for a specific custom processor can be developed very quickly. We are also developing the reference IP models and reference virtual platforms. We already have a virtual platform for Sci-Fi FE310 SoC and we are in the process of developing the virtual platform for various open source SoCs like CoreV MCU from Open Hardware Group or CoreSwerve OLF from the Chips Alliance. So these reference IP models and virtual platforms can act as a very quick start for developing the model for any RISC-V based SoC. Today, no one has any doubt that ESL has to be the essential component for the design and verification flows. But there are several challenges in the effective adoption of ESL. ESL requires very unique combination of skills, which is the hybrid of computer science and semiconductors. And there are very limited number of professionals with the right kind of expertise. System C is a very versatile language. Using it, you can develop the models at a very high abstraction levels, which are as fast as the hardware, or you can develop the models which are very accurate but very slow as the RTL. So just learning the language is not sufficient. I mean, you need to learn the modeling techniques for the specific use case. At Circuit Sutra, our mission is to accelerate the adoption of ESL methodologies in the industry, and accordingly, we have designed our offerings. We provide SoC modeling services, and as part of it, we set up the world-class project teams to work as the extension of the customer's R&D team remotely through offshore development center or on-site at the customer location. We also have a reusable system C modeling IP and methodology, which helps the customers to get started quickly with their modeling projects. As part of it, we have a Circuit Sutra modeling library, which is a boost-like utility library on top of System C. We have virtual prototype quick start packages, which have the TLM sockets and reusable modeling infrastructure for various popular communication protocols. Plus, we have lots of reference IP models and SoC virtual platforms. We also have a highly effective training System C modeling for virtual prototyping. With 15 plus years of 100% focus on ESL domain, we have gained very in-depth understanding of all the aspects of ESL, and with that we are able to support our customers in the effective adoption of ESL methodologies. Thanks for attending this session today. In the next presentation, Swaminathan from our team will be presenting in detail about the ESL methodologies for architecture exploration.
Architecture exploration is the process of identifying the optimal architecture to map a given design or a use case, respecting the design constraints. In today's talk, we are going to have a look at the role ESL plays in architecture exploration. My name is Swaminathan and I'm currently the Director of ESL Technologies at Circuit Sutra. So, how do we do the architecture exploration? In order to do that, we make use of performance models, which are detailed models which model approximately timed or cycle accurate TLM models. The transaction level models also include the memory subsystems, the interconnects, etc., which are modeled to some certain level of detail so that we can extract metrics like the latencies, throughput to make sure that it matches our expectations. Nowadays, just having the performance numbers aren't enough. The key word here is performance per watt. So to have a sense of the power numbers is also important. In order to support that, we make use of System C or TLM models, which also capture the power intent of the different IPs which go into the architecture model. Accelera has a standard called UPF or Unified Power Format, which makes use of legacy measurements for the various power numbers and plugs it into the simulation so that we can get a sense of what are the power numbers for this simulation. One of the things which can help us with the modeling is to have a declarative System C syntax, which essentially once you have a functional core, right? For example, if you're doing an encoding or decoding, you have a C function which takes in all the parameters, performs the computation, and then generates certain output. Now, the function alone isn't much use standalone. Rather, it needs to be fitted into the entire system to see during the simulation if there are any bottlenecks, etc. And to do that, the C functions have to be wrapped in a System C format so that it can interact with the rest of the virtual platform. So here, instead of doing System C modeling from scratch, we can make use of such declarative System C infrastructure, which can be built to ease this process. Another thing which can help us in architecture exploration is a TLM bus kit. As you might be aware, transaction level models are very generic models for modeling memory mapped bus transactions, right? But when you are modeling at an architecture level, usually the specific buses which are going to be using are also kind of determined. So you need to be able to model the latencies and other quirks of that particular bus. To do that, we'll have to specialize the TLM for the specific bus protocol that we use. And going forward, let's say we decide on this architecture, instead of modeling it at a very detailed but slow process, it should be possible to simulate the same system at a higher, let's say TL4 level. So can the bus automatically switch from a detailed simulation to a higher level TL4 level simulation? To help with those things, having a TLM bus kit is very useful. It is not these infrastructure. There is also open source infrastructure. For example, the GEM5, which is an open source simulator for architecture exploration. It has a lot of features. We will look into some of them in the coming slides. So finally, we are going to also look at what are these application workloads and how they can be mapped onto the different architectures that we want to explore. Usually by running traces of the application on the specific system that we have chosen, and how can we extract the performance numbers from that. Let's take a look at the modeling infrastructure for architecture and performance modeling. One of the first things that we are going to take a look at is a declarative syntax for wrapping around purely functional cores. So when we typically see a system architect or a domain expert, and let's say they are coming up with an algorithm for, say, encryption, decryption, etc., they make an assumption that the data is kind of available, and they go ahead and write a C function, take in all these inputs as parameters, perform some computation, and generate the output as output parameters. Now, if you want to get the full leverage out of this particular algorithm, you need to be able to fit in the context of a system simulation. Now, the architects themselves may or may not be experts in wrapping it up with system C and plugging it into a virtual platform. So how do we kind of ease the process? So for that, we have come up with this declarative syntax. If you look at the diagram on the right, we have a box which has a computational unit called A. There are two inputs, 1 and 2, and it generates an output 3. Let's assume A is just max 2 or max of two numbers, two input numbers, and it generates the max of those two in the output. So here we have provided a sample code snippet, like how you can take a simple function called max2 and how you can write a simple declarative syntax for that. And this actually transforms to an SE module with the corresponding SE inputs for the two integers which are coming in, and an SE output for the max of those two numbers. And the computational unit is automatically triggered once both the inputs are available, and it generates the output. In order to kind of support a variety of different modeling scenarios, the infrastructure is divided into three types of components. So one is the component that we have seen, which is the final atomic unit which carries out the actual computation. And then you have the blocks. The blocks themselves don't have any code, but they are in turn composed of other components and other blocks to provide the desired functionality. The subsystems are very much like blocks, but they have further restrictions with respect to what kind of interfaces they support at the boundary. For example, say memory TLM2 ports. So here is a diagram which shows a component, a block, and a subsystem, and how it could internally be composed. In addition to this, we also support a mechanism for computing architecture level parameters, for example, power, area, etc. And these can be specified hierarchically. And you can also provide a function with respect to how you want to aggregate these parameters at a subsystem, at a block, or a subsystem level. So to go further, we don't necessarily need only these custom built blocks or the specific functional blocks. In addition, there needs to be a lot of plumbing around it. So we have utilities like a generic trace driven traffic generator to drive traffic into the system to carry out further analysis. You also need elements like a FIFOs, line buffers, ring buffers, mux, demux, selectors, forwarders, etc. in order to construct the system. And instead of doing code-based corrections like writing C++ or System C code, this same connectivity could also be done using a simple text-based description. A simple CSV file says what is a port and what are the port or ports you want to connect it to, and any intermediate components like channels, etc. would be dynamically instantiated and the connections done. And the best part is this infrastructure plays well with the existing simulation tools, for example, Platform Architect. So what are the advantages of such a syntax? One of the main advantages that we have seen is a greatly reduced development time. As you see, once the functional core is available, you can quickly do a declarative syntax and bring up the corresponding System C IP block for that particular functionality. And you obviously have to write lesser number of lines of code, which is already debugged and used in multiple contexts. So lesser lines of code kind of corresponds to lesser bugs introduced into the system. And if there was any concern, the simulation speed of such blocks are on par with hand-coded IP blocks. So you don't suffer any degradation or anything. The speed is about the same as what you do if you hand-code the same functionality. Moving on, we are going to look at the TLM bus kit for a proprietary SoC bus modeling for architecture or performance analysis. What is the need for such a bus kit? When we are doing architecture analysis, we are early in the cycle and we are yet to commit to a certain ISA or a certain memory bus. We want to select the right bus which satisfies our bandwidth, latency and power requirements. So there are two concerns here. One concern is we want to preserve the user level code so that if we decide to go ahead and try out a different bus, we shouldn't have to change the user level code. And secondly, the abstraction at which we are modeling the buses. We should be able to model the bus at a higher level of abstraction, providing us greater speeds, or at a lower level of abstraction so that we get more accurate representation of the bus protocols. So let's look at how this can be achieved. This is achieved by creating a convenience socket so that the user facing APIs remain same irrespective of which protocol you decide to use or irrespective of which level of abstraction you decide to use. So thereby you are preserving the user facing code from any changes. So within the convenience socket, we instantiate a transport socket. Now this transport socket implements the bus specific FSMs. And here there are a couple of more things to understand. So when we talk about transaction level modeling, it describes broadly two kinds of models, a loosely timed model for fast simulations and an approximately timed model which is transaction level accurate and which is used for more detailed modeling requirements. Similarly, the OCPIP consortium has defined 5 levels of abstractions ranging from TL4, which is the most abstract, to TL0, which is the most detailed level of modeling which matches the RTL behavior. So if you try to compare the TLM terminology and the OCPIP TL terminology, the TL4 level roughly corresponds to the TLM LT style of modeling. Here the entire burst is transmitted as a single entity and there are just 2 timing points. If you look at TL3, it corresponds to the TLM 2.0 approximately timed models. Here also the burst is transmitted as a single entity, but instead of 2, now we have 4 timing points for better control. And finally, at a more detailed level in terms of architecture modeling, we have the TL1 level wherein we break down the burst into individual beats, which is also based on the bus width. and each beat is transmitted as a single entity and it carries many more timing points. In the next slide, we are going to have a look at the different TL levels and how the bus transactions happen. So here, as we can see on the leftmost, we have the TL4 or the TLM 2.2 loosely timed modeling, where the entire transaction is sent in one shot, and on the return path, the transaction ends. If you look in the middle diagram, we have the TL3, which is also equivalent to the TLM 2.0 approximately timed style of modeling, where we have 4 timing points: begin, end request, begin, end response. On the rightmost side, we see the TL1 or the TLM 2.2 cycle accurate modeling, which is the most detailed models. And here we have many more timing points where we have extended the standard TLM 2.2 timing points to accommodate the bus specific protocols. So here you see that the burst is broken down into individual beats. So over the last 2 slides, what we have seen is the need for a TLM bus kit, which can help us model these memory map transactions with little or no change to the user code, at the same time providing us flexibility to model specific bus architectures. Also, another feature which this kit provides is the ability to dynamically switch from a TL4 level of abstraction to a TL1 level of abstraction, or vice versa, depending on the accuracy or speed needed for that simulation. GEM5. So there are multiple open source solutions for architecture exploration, but the most popular of them is GEM5, which is a modular discrete event simulator platform. All right. So it can simulate a complete system plus the operating system which runs on that platform in 2 modes. One is the full system mode and other is the SE mode or the syscall emulation mode, which can run only the user space programs. And the GEM5 environment, it supports different ISAs like x86, ARM, RISC-V, etc. And the models include simulations at different levels. For example, single CPI models or out of order models, or even in order pipeline models. So it supports the different types of modelings as well. And the processor itself is of certain utility. Combined with the memory system is where it gets a lot of its power from. And the memory system can also be very flexibly built out of its the built-in memory system like Ruby, which it provides, and which is very configurable. So if you look at GEM5, once the GEM5 ISA is built, the binary takes a Python script as an input. So what does the Python script contain? It contains instructions for how do you construct the system, as well as it also contains instructions for running the simulation and collecting the traces. And another thing which GEM5 supports is doing power aware simulations. We did talk about how getting the power intent and the power numbers are also important. So GEM allows us to capture the power details during the simulation process. And because System C has also very wide acceptance in the industry, and a lot of people want to do GEM5 System C co-simulation. So GEM5 has libraries which allows the GEM5 simulation to run on top of the System C event-driven core engine, as well as talk to System C TLM sockets. So it has all these helpful library support as well. Let's delve a little deeper into the power model to see what are the kind of overview of what are the different power models or power types that it supports. So in order to do the modeling, so we can divide the system into different clock domains. So we have the clock domain and then hierarchical clock domain, like a source clock domain or destination clock domain, derived clock domain. And then we have voltage domains across the system. and each voltage domain is associated with a clock domain. And we also have thermal domains which also talk to the voltage domains as well. So if you look at what are the different power states which are supported for an IP which is modeled within the Gem5 context, it can take any of these 5 states. The first one is undefined, wherein you don't know anything about the power state within that particular IP. 2, where the IP is on and operating at full capacity, or if the IP is clock gated, or if it supports some kind of retention like SRAM. The memory, some of the memory and registers are retained even if the clock is gated, and of course when the IP is switched off. So if you look at the power types, there are 2 kinds of power. One is a static power, where whether the system is running or it's off, it still consumes that amount of power, which is called the static power, and the dynamic power, which is consumed when the IP is performing some kind of action. So if you look at the total power of the system, it is a combination of, or the weighted average of, the time spent in the static power state as well as in the dynamic power state. So when you combine them, you get what is the power consumed by that IP. Now let us take a look at the Unified Power Format 3.x, which is also the IEEE standard 1801 2018 revision. One of the primary intents behind the UPF standard is to enable the portability of the power intent across a variety of products and throughout the entire flow of the electronic system design, implementation, verification, etc. It's important to see that the UPF files are also a part of the design source as much as the RTL. It provides a complete design description where the RTL indicates the logical intent and the UPF indicates the power intent. In order to extend the traditional simulation to include power, we need to annotate the power information onto the simulation. And the way to do it is to use of system level IP power models. So you see on the right, we have a traditional IP host based model, and then you have the power model latched onto it as a slave module. So these models, the power models, cannot directly make any change onto the state of the IP host model. It can only communicate through the IP host model to which it is connected. So it does not directly talk to other power models corresponding to other IP models as well. Now let's take a more detailed view of the UPF and what it enables. One of the primary reasons for it to exist is to abstract out the power behavior of a component, not make it very specific at the very beginning when we are starting our exploration. This format also allows us to specify the different power states as well as the power consumption associated with each state. For example, if you consider a CPU power model, it can have states like active, sleep, idle, with different power consumptions in each of these states. So we could allow these power consumption to be represented as just a list of floating point numbers corresponding to each state, which is static, or we could also do the power consumption dynamically based on voltage or frequency or other relevant parameters, so that it is more accurate with respect to the final simulation. The best feature of the UPF 3.x is it allows successive refinement of the power specification. We can start off with a very abstract listing of the power specification, and as the project moves ahead, as we get more information, we can start annotating those details into the same power model. And please note that it enables power consumption calculations with realistic application workloads and not just some kind of Excel calculations, but when we are simulating the realistic workloads, we are able to do the power consumption calculation side by side. And it also enables the power management policies and the partitioning of the SoC power domains quite early in the cycle. When we look at UPF 3.0, one of the things that it also allows is the complete automation of power aware, static and dynamic checking entirely through tools. We don't have to eyeball complex logs or other things to figure out. It allows the complete automation of this entire step. Also, it also allows automation of power aware functional coverage, which was not possible earlier, by capturing all the relevant details and logging it into the UCDB or the Unified Coverage Database. So what we have seen over the last two slides is that UPF specification provides the foundation on which we can now add power modeling information onto the traditional simulation or architecture exploration flow. So finally, we are going to look at how an application workload is going to be executed on a System C platform and what purpose it kind of serves. So if you look at a workload, essentially what it tries to do is to model what is the actual load which is going to be put on the target system when a specific application or a use case is going to be run on that particular system. And it's very important that the workload reflects the correct control structures of the applications in terms of input, output, processing. It needs to capture the control part correctly. And if you look at the computation as well as the communication load on the system, these are usually derived from traces of the application which are captured in a different platform or through earlier simulations. So here is a simple flow chart. On the left hand side, you are able to see the use cases and applications that we want to try out. And from these use cases and applications, we try to extract the corresponding workload model. So it could be captured in UML format or some kind of a data flow format or task graph, can't process networks, etc. On the right hand side, you try to see what are the execution platforms on which you want to try out this particular use cases, right? And from these, you derive the corresponding platform model, which are usually written in System C. Then you try to map the workload onto a specific platform by allocating the resources to whichever IPs satisfy the constraints of that particular workload. Once you've done the task allocation, then you try to simulate the particular use case, and through the process of simulation, you try to collect the traces, and then you do the post processing of the traces to see whether this particular architecture is supporting your use case, is supporting your power constraints, and it also supporting your design constraints or not. So through this presentation, what we are trying to see is, in the field of architecture exploration, how you have performance models, how you have power models, how you can make use of infrastructure like a declarative syntax for wrapping around the functional models into a System C kind of a framework, how you can make use of toolkits like the TLM bus toolkit in order to support different bus architectures without having to change the code that you write for a specific bus through convenient sockets. And then we have also looked at an open source solution like a GEM5 platform, which kind of allows you to simulate different kinds of ISAs. It also has a very flexible memory system configuration, and models written in GEM5 can also interop with System C models nicely. And then finally, we have also looked at the application workload and how these application workloads are mapped onto the platforms on which we want to run the specific workloads, and how after simulating in the platforms we collect the traces and then perform the analysis to see whether we are able to arrive at the right or the optimal architecture for this particular use case or not. So thank you so much for your time. I think this would be my last slide. Thank you.